Welcome to our discussion on the chain rule. This is where we learn how to take derivatives of more complex looking functions. If you think about an onion and peeling off the layers of an onion or peeling off the layers of an artichoke or your favorite vegetable analogy, that's how the chain rule works. We're going to basically take derivatives of layers of functions. So as long as you can think of a function as a composite of other simpler functions that we know how to take derivatives of, then you can take the derivative of anything. For instance, we've got this function here, the square root of x squared plus 1. And so far, we don't know how to do that. We know how to take the derivative of just the square root of x because that's just a power of x, and we can use the power rule. And then, of course, we know how to take the derivative of x squared plus 1 because, again, that's just powers of x, right? It's a polynomial, and we can use the power rule for that. But how do we handle a combination of the two? Well, as long as we can see that this is really a composite function made up of the two simple functions that we do know how to take derivatives of, the square root of something, and then a polynomial, then we can write this function as a composite function, an f of g. And then we can use the chain rule to basically take the derivative of each of those simpler functions as layers of this composite function. And it doesn't have to stop at 2. We can have 3 layers, 4 layers, 5 layers, it doesn't matter. So as long as you can think of something as a simpler function that's doing something else to another simpler function and so on and so forth, you can use the chain rule. The chain rule seems to come from reducing fractions. This idea down here at the bottom that dy dx is just dy over du, right, times du dx, and then you think, well, if you multiply fractions, the du's cancel and you get dy dx. And that's basically where the idea comes from. Remember that this doesn't actually work, right? These aren't really fractions. You really don't multiply them. You really don't cancel. But theoretically, it works that way because derivatives are rates of change, right? dy dx is how fast y is changing with respect to x. But if we know how fast y is changing with respect to u, and then how fast u is changing with respect to x, the change in y with respect to x is just going to be a multiplicative property of those two. And it's very simple if you think of it this way, right? If u changes twice as fast as x, so there's our first piece here. So every time x goes up by 1, u goes up by 2, right? So we have x goes up by 1. This causes u to go up by 2. Well, if we also know that y changes 3 times as fast as u, then every time u goes up by 2, that means y has to go up by 6, right? Because it's 3 times as fast. So therefore, we can see that it's very reasonable that y changes 6 times as fast as x, right? Y goes up by 1, u goes up by 6, and then dy dx is going to be 6, which would have been dy du. Remember, they told us that y changes 3 times as fast, so dy du was a 3 to 1, right? 3. And then du dx, u changes twice as fast as x, and you multiply those two together, and that's where you get that rate of change of 6. Here's how the chain rule works in its definition form. If you're taking the derivative of some function, you basically take the derivative of the outer layer. Remember, we're going to define all of these functions now as a composite function, an f of g. And again, this can go on forever. It can be f of g of h of j of k and so on and so forth. When you're taking the derivative of the big f function, right, the normal function, what you're really doing is first, you're just taking the derivative of the outside function, and you'll notice that the inside function doesn't change at all. It's still just g of x. And then the second step is taking the derivative of the inside function, and you get the product of those two. Because taking the derivative of the outside function is giving you this. Taking the derivative of the inside function is giving you that. And when you take their product, that's how you get the dy dx. Now you can write this in whatever notation you want, but the idea is still the same. It's the derivative of the outside function with the inside stuff held constant. It doesn't change at all, right? Because we're only concerned with the change in the outer function. And then you multiply that by the inside function changing. And you just keep doing that until you get down to dx dx, basically. So let's revisit the example we saw at the beginning. We can think of this function as f of g of x, right? Where f just equals the square root of something, and the g function is the x squared plus 1. Well, they tend to use f with a different letter to kind of remind you that you're doing a change in u, right? And then you do it's kind of like a u substitution. You can do that if you want. It's really not necessary. The idea is still the same, right? To take the derivative of this outer function, you're just taking the derivative of the square root function. And that is x to the 1/2, which becomes 1/2 x to the negative 1/2, which is 1 over 2 square roots of x. And that's where this piece comes from. And you'll notice there's just 1 over 2 square roots of x. But instead of x, it's the stuff that's actually inside of it, right? It's that u substitution. They're letting u equal this x squared plus 1 thing. Then you come along and take the derivative of this piece, which is very simply just 2x. That goes up on top, the 2's cancel, and that's why you get this as your final answer. Okay, now using the dy over du times du over dx notation, you'll see is really the same thing, only you're using you're actually writing in a u and then you're subbing it back out later. If you want to use formula 3, you just have to bear in mind that dy dx refers to the derivative of y when we consider y to be a function of x. So that's the derivative of y with respect to x, whereas dy du is the derivative of u when we think of it as a function of u, and thus we're looking for the derivative of y with respect to u. And with that in mind, in example 1, we could have considered y to be a function of x, but we could also consider it to be a function of u and do that whole kind of u substitution thing. Either way is going to get you the same result. Bottom line is you don't have to really do the whole u substitution thing if you just think about it as these layers of an onion, right? You're first taking the derivative of the outside layer, then you move in and take the derivative of the inside layer, and you keep going inner and inner to further and further down until there aren't any layers left. But if we want to do it this way, right, we can look at another example. Let y equal sine of u, where u is some sort of differentiable function of x. Then by the chain rule, we know that if we want to do dy dx, we first have to do dy du, and then figure out du dx and take the product of those two things. Well, the derivative of sine is very easy. It's just cosine, so that becomes cosine u, and then du dx. So therefore, the derivative of sine u is just cosine u du dx. Another simple example we can think of, something that we already know how to do, is we know that the derivative with respect to x of e to the x is just e to the x. But what about the derivative of e to the x squared? Well, if we think of x squared as our u, then this really becomes the derivative with respect to x of e to the u. Well, we can't really do this, so instead we have to do the whole d du times du dx of it, right? And d du is just e to the u, that doesn't change. And then du dx means we're taking the derivative of this with respect to x, and the derivative of that is 2x. And then if we sub back in, because we want to write it all in terms of x, we see that we just get e to the x squared times 2x. And you can now see that if you want to take the derivative of e to any function of x, it's just going to equal e to that function of x, you see how that didn't change, times the derivative of that function of x. Very common usage of the chain rule. All right, here's another example, the power rule. Very common, another common usage of the chain rule is to apply it to the power rule, but this time instead of x to a power, we're now going to have a function of x to a power. So just like I looked at the e to the x and then the e to the f of x example before, we can now have a function being raised to a power. All right, so we've got this g of x to n being our y. Right, y is some function raised to a power. Well, we know if we just think of that as a function of u, right, we can just write it as u to a power, where u is this g of x. Then using the chain rule, if we're trying to take the derivative with respect to x, we're really taking the derivative with respect to u and then multiplying by the derivative of u with respect to x. All right, the derivative with respect to u is just using the power rule, and u to the n minus 1, and then du dx. Well, in this case, that's just the derivative of the function. And this is where we get our generalization. If you have some function raised to a power, you run the power rule, then you multiply by the derivative of the inside. It's just a chain rule applied to a specific type of problem. So don't think about, oh, now I've got to memorize this, and oh, I've got to memorize the e to the f of x. No, you don't, because these are all just special versions of the chain rule. Just remember you're doing the chain rule. Here's another example where we have this function raised to a power, right? You recognize this as, hey, look at this is just something raised to a power, right? This is my u to the n. So by the chain rule, the power comes down, and then it's the power minus 1 times the derivative of the inside. So the derivative of the outside is where you get the 100 and the 99, and then the derivative of the inside is where you get the 3x squared. And then you just put it all together, right? We don't normally leave a constant here by itself with some more junk on the back end. We put it all together, put it all in front, and then our final answer is that. Okay, we can also apply this to not just e to the x, but a to the x. We've already kind of seen that as we took derivatives of different numbers to the x, we ended up getting that, like we did 2 to the x and we got, I think it was like 0.69 2 to the x, and then we did 3 to the x and we got 1.0 something 3 to the x, and we looked at a couple others and we noticed that it was always still a to the x but then times some number, and it turns out that number always ends up being the natural log of the base, which is why when you take the derivative with respect of x of e to the x, you just get e to the x, because technically you're getting e to the x times the natural log of the base, but natural log of e just equals 1, right? So again, this is just a more generalized formula for what you already knew in terms of the derivative of e to the x. Here's a simple example. As I said, we've seen this before, that we knew that it was roughly 0.69 times 2 to the x, but this is why, because natural log of 2 is 0.69, blah, 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 blah. Okay, lastly, I said this before, we can expand the chain rule really to an infinite number of functions. It doesn't have to stop with just 2. We can do it to 3, 4, 5, and so on. So no matter what you have, no matter how complicated it looks, if you can think of it as a function inside of a function, inside of another function, inside of another function, and all of those, layers that you're creating, the layers of the onion, if all of those are simple functions that you know how to take the derivative of them, then it's very simple. You take the derivative of the outer layer, leaving all of the inner layers alone. They don't change at all, right? You're holding them constant. Then you multiply that by the derivative of the next layer in, right? The second layer, with everything else inside of it being held constant. And then you multiply by the derivative of the third layer in, with everything else being held constant, times the derivative of the fourth layer and the fifth layer, all the way down until you're out of layers. And that's the chain rule, guys. It's really simple. Don't overthink it.